All right, so we should be recording now. Did everyone in the Zoom just get like a pop-up that says this is being recorded, basically? That should be the case. Welcome everyone to this study session. This is for PHY2048, aka Physics 1 with Calculus. With that being said, I did want to go over some disclaimers. First of all, 1, no, I'm not a TA. 2, no, I'm not a professor. Therefore, yes, there are things in this presentation that could theoretically be wrong. So if you guys notice something that you think is wrong during the presentation, please do not hesitate to just tell me, because I don't want to accidentally, spread misinformation. That's not the goal here, obviously. So keep that in mind. With that being said, I'm still going to do to the best of my ability, try to refresh you guys on a lot of the topics that we've learned here in 2048 for this first exam. How I've basically structured this is I've gone through the 3 previous semesters exams that we've been given, and I've basically taken a collection of the more difficult or conceptually challenging questions. And my plan is to do those questions with you guys and explain the processes. And once again, it's more focusing on the conceptual knowledge so you guys can understand how to do that on our real exam tomorrow. So yeah, I'm just going to start off. You can see our wonderful introduction slide. It's a little bit of a plain slideshow this time around because most of the stuff is just going to be me drawing. So I decided white background makes sense that you guys can actually see what I'm doing. All right, so here's our first question. Big brain idea. I should get my calculator out because we're going to need calculators for a lot of this stuff. So let's see. Here's my calculator. I believe we are allowed to use graphing calculators, but they just can't be ones that can connect to the internet. So keep that in mind for tomorrow's exam. I'm not 100% sure if a TI-84 is allowed or not. I'm probably going to ask before the exam. He said yes for TI-84? Okay. Okay, cool. Somebody in the audience, for you guys on the Zoom, said that they asked and he said a TI-84 is allowed. Okay. TI-84s are nice, by the way, because they have built-in quadratic solvers, just so you know. So we're going to get started with this question, okay? It says, and this is a dimensional analysis problem. This problem, dimensional analysis really is more used when you're solving other problems that use dimensional analysis, but to know its basic roots is very important. And I can guarantee you that there will most likely be at least one dimensional analysis problem on the actual exam. So it says that remembering that there are 2.5 centimeters in an inch, and of course 12 inches in a foot, and 3 feet in a yard, how many square centimeters are there in a square yard? So now you might think that since it first says 2.5 centimeters, oh gosh, what did I do? Got to go back. Let's see, got to click this so that we can draw. There we go. You might think that since it says 2.54 centimeters, we're starting with centimeters and then going somewhere else. But that is actually not the case. We're actually going to be starting off with, it says in a square yard. So we basically have 1 yard squared over 1. That's what we're going to start off with. Okay. So the easiest thing to go from a yard to, if you guys don't know, is a foot. Now, yards is on top. So we're going to have to put a yard on bottom now so we can cancel out the units. So we're going to go 1 yard is what, 3 feet, right? So now, does anybody see an issue with this? There's a slight issue here. If we just did this conversion, well, yes. Right. So this yard, what he was saying in the audience, for you guys on Zoom, this yard is squared. And notice that this yard on the bottom is not squared. So if we were to just do this math and say now we're in feet, that's an issue because we're not actually going to be in feet. We're going to be in feet per yard or something. So in order to get rid of another yard, the easiest way to do that is actually to square this. And now notice now we're going to go from yards squared. Yard squared is going to cancel out. And now we're going to be in feet squared. Okay. Does that make sense to you guys? Hopefully. So then after that, we're going to go from feet squared to inches squared. So we know that we're going to put feet on the bottom, and 1 foot is going to be 12 inches, right? So basically, now we have gone from feet squared to inches squared, and we're going to centimeters squared. So then we just have to use the conversion factor for centimeters, which it tells us that there's 2.54 centimeters per inch. So now we're going to go and we're going to say, let's see. So then we're going to go 12. So we're going to put 1 inch on the bottom. And we're going to put 2.54 centimeters up here. And then let me solve this and make sure we get the correct answer. So we're going to go 1 times 3 squared times 12 squared times 2.54 squared, we get 8361.27 final answer. And notice that also, just so you guys know, for every single question, because these practice exams were taken from the answer key bank, the answer is always just the first option. So notice that for this, our answer was 8,361. That is approximately 8.4 times 10 to the third. Does that make sense to you guys? Hopefully that process of dimensional analysis in general, like you should be able to do that process no matter what units you're converting to, but that's the basics of this process for just any type of question that goes like that. So now I'm going to move on. Dot products and cross products. This is where it's actually time for me to teach you guys some stuff, because for those of you who have already taken Calculus 3, you'll look at this, and you probably already know the visual trick, and that's what I'm about to teach you guys is with you. For those of you who have not taken Calculus 3, I'm about to show you a visual trick for this. That basically makes it so that when you do dot and cross products, you don't have to look at that big nasty formula, because that thing is really intimidating, and it's probably also very confusing. So we'll start with the dot product of these numbers. The dot product is actually pretty easy either way. So if we have also, by the way, just so you guys know, for these vectors, like this orientation where you have the brackets and then a 1, 2, 3, this actually means, I'm going to mute all the users. There we go. So what this actually means is this means 1i, go back. All right, this means 1i plus 2j plus 3k, just so you guys know. That's what that, this is just a different way to write a vector. But so we have this vector. We're going to do the dot product first. Basically, what we're going to do is we're going to write it out like this: 1, 2, 3, dot, 4, 5, 6, right? And then we're basically going to match these up based on their components. So like this is an I, this is a J, and this is a K, right? And then this is an I, this is a J, and this is a K, right? So we're going to multiply the I by the I. We're going to get 4. We're going to multiply the two J's together. We're going to get 10. And we're going to multiply that, the two K's together. We're going to get 18. That is 10 plus 18, which is 22, plus 4 is 32. So that is our final answer for that dot product, okay? Notice when we do the dot product, we get a scalar quantity, which basically means we do not get another vector. We get like an actual number. So now we're going to do the cross product of these two. And when we do the cross product, I'm going to go show you guys a visual trick to help you do cross products a bit easier, rather than using that super huge formula. So first, what you're going to want to do when you take a cross product, you want to write them on top of each other. So here's the top one, and we're going to do this 4, 5, 6. So, oh gosh, let's see, eraser. We're going to go 4, 5, 6, right? Here's the cross product, right? But actually, what we're going to do, we're not going to do that. We're going to write them on top of each other. So it's going to be like this. So now there's a trick, right? So we know that this cross product, right, is going to be some form of x, y, and z, right? We know that it's something. Now, for doing these cross products, whenever you do a cross product of any sort, the x, y's, and z's, they're going to alternate signs. You won't learn that in physics or really in Calc 3. Supposedly you learn this more in depth than when you're algebra, but basically we just need to know that these are going to alternate signs. What did they do? No, back. X. Okay, so we're going to know that this is positive, this is going to be negative, and this is positive, right? Just keep that in mind. This is for any cross product. So the trick here is, first we're going to start off with the x's, and what you're going to basically do is you're going to go to your cross product, and to start off with the x, you're going to basically make the current x's invisible. You're not going to pay attention to these, okay? Those are bad. We're just not going to look at them for now. Okay, so we're going to basically just look at the y's and the z's. And then what you're going to do is you're going to take this right here, and we're going to start writing it out. So we're going to look at the x's instead of the y's and the z's, and we're going to take this one and multiply them together. So we're going to get 2 times 6. What's that, guys? 12, right? So we're going to get 12. And then we're going to look at the other two diagonals, this one, and we're going to actually subtract those. So we're going to get 12 minus 15. And then, okay, the crazy idea, what if, theoretically, we did the exact same thing, but instead of doing that with the x covered up, we did that with the y covered up. However, we also need to remember that it's negative as well. So we're going to cover up the y. Just going to completely ignore that for now. And now we're going to do 1 times 6 is 6, minus 4 times 3 is minus 12. But once again, remember that it's negative for this one. So is it actually 1 times 6 minus 4 times 3? Well, no, it's actually going to be 4 times 3 minus 1 times 6. So it's going to be 12 minus 6. Did you guys see what I just did there? Like basically saying it's flipped this time around because it's negative. So 4 times 3 is going to be 12 minus 1 times 6, 6, okay? And then after that, what we're going to get is we're going to do this one more time, but with the z direction. And in the z direction, once again, it's just going to be positive. So it's just going to be that normal, what I did earlier, but we're going to cover up the z. We're basically going to say 1 times 5 is 5. And then minus 2 times 4 is 8. So this is what we get, okay? This is our final cross product. So then if we just simplify this, we get negative 3. That was a really bad negative sign. We're just going to get negative 3, 6, negative 3. So that would be our final answer for the cross product of that vector. And I wanted to show you guys that method of covering it up. Now, if this just confused you more and you'd rather use the formula, that's obviously perfectly fine. You're still able to do that. However, that's just a visual trick that I think makes it a little bit easier, basically, to do it, especially if you have paper in front of you. If you learn that trick, it's pretty easy. Now, after this, you might actually be told to find the magnitude of the cross product, which would be denoted something like this. If you're told to find the magnitude, basically what you're going to do is you're going to take all these values and you're going to square them and then add them in a square root. But it's kind of like Pythagorean theorem, just now we're in 3D here, so there's 3 values instead of 2 values. So 3 squared is 9, plus 6 squared is 36, plus 3 squared is negative 3 squared actually is 9. So we're going to get the square root of 54. And then the square root of 54 is like the same thing as the square root of 9 times the square root of 6. So you're going to get 3 root 6 would be the magnitude of that cross product, if that makes sense. So then we're going to continue on. Yeah, what's up? If they only, okay, so you're saying—
What up, party people?
We're going to have to mute everyone again, I guess. That's crazy. But anyways, so yes, you actually can. And I'm actually literally in the next problem, I'll show you how to do that. Because like the next problem is an actual problem where you only have the I and the J. So yeah. So let me go back to the presentation. And so does anybody have any other questions on just how to generally do this or no? Yeah. Oh, okay. I can show you. So if you have the cross product, right? Basically what it's saying, it's if you have, let's say you have like a Y direction and an X direction, right? What the cross product is saying is we're finding, so this could be a vector and this could be a vector. We're finding another vector that's perpendicular to both vectors at the same time. So it might be like this type thing. And basically, if you look at like, it's going to be like whoop, and then it's also going to be like this. It's like really hard to draw because it's 3D, but like that's like a completely different direction, basically. So like this could be like, I don't know, a Z direction or something. But basically, they're all perpendicular at the same time. Once again, in Calc 3, you'll use that to find like planes and stuff that are like of different directions. And you might use it for like different, when you're doing math on like other fields of forces and stuff. So yeah. That's that. Any other questions or no? Okay, cool. I'll move on. So here's an actual physics problem. This was from a previous exam, I think spring 2019. I could be wrong though. So it says there are 3 vectors, 3i plus j, b equals I plus 3j, and c equals I plus 2k. The angle between the directions of c and a cross product b is in degrees. Now this goes to a few formulas that I need to mention to you guys. First of all, just so you guys know, if we have some vectors, right? This is completely separate. These are just equations that I want to show you. For a cross product, we have a dot b This is equal to the magnitude of A times the magnitude of B times cosine of theta. And if we have A, the magnitude of the cross product of A times B, this is equal to A, the magnitude of A times the magnitude of B times sine of theta. So keep these in mind. These are very important for general use cases. These are very important formulas to know. You can use either one of those when doing this problem. It doesn't really matter. Just do whichever one you find easier. And honestly, the the dot product is usually easier, just so you guys know. So anyways, we have A equals 3i plus j. I'm going to write this. Now, what I'm going to do is I'm going to write this as a 3D vector in the bracket notation. So this is going to be 3, 1. What happens if we don't have a k here? What if this is 2D, guys? What would k be? 0. So this is the same thing as writing a 3, 1, 0 vector. Okay. And then same thing for over here for B. So this is actually A. And then there's B, right? If we have B, what's that? Is it just any guesses? Somebody answer it. 1, 3, 0. Okay. And then we have C, right? And I'll write C out here because we're not using it until later. C is going to be 1. Now notice there's no J, so that's just going to be 0 for the Y, and there's 2 for the K. Okay. So then here are our 3 vectors we have. It's first telling me to find the angle between C and A cross B. So first we're going to have to find A cross B. We're going to have to figure out what that is. So we're going to do a cross product. When we do this cross product, gosh, I keep opening this thing up. There we go. When we do a cross product, once again, we're going to cover up the X, and we're going to see that it's 1 times 0 and 3 times 0, so that's 0. And we're going to cover up the Y, and we see that it's 3 times 0 and 1 times 0, so that's also 0. And then for this case, for the Z, it's going to be 3 times 3, which is 9, minus 1 times 1, which is 1. So it's going to be 9 minus 1 equals 8. Hopefully that makes sense. And I'm speaking kind of fast, but you can see how that's 8. Now notice, when we do this 2-dimensional cross product, we only ever get basically 1 dimension in the dimension that we aren't using. So the cross product for A and B is just in the Z direction, just 1 component. Notice that. But we can still treat this the same as a 3-dimensional cross product. So now we have 0, 0, 8. And then we're going to have to find the angle between this vector right here and C, which is this vector right here. So now we can look at our formulas, and I'm telling you right now, it's easier to do the cross or the dot product formula. So what I'm going to do here is now I'm going to bring 0, 0, 8 here. I'm going to dot product it with 1, 0, 2. And then, so if we were to take the magnitude of 0, 0, 8, right, it would be, I'll try to write it small, it would be 0 squared plus 0 squared plus 8 squared, which is actually just 8. So put 8 here. If we were to do the magnitude of 1, 0, 2, it's going to be 1 squared plus 0 squared plus 2 squared. You get root 5. And then we have cosine theta because it's a dot product. So then what we're going to do, we can see that 0 times 1 is 0, 0 times 0 is 0, 8 times 2 is 16. So we're going to have 16 is equal to 8 root 5 cosine theta. And we're going to have theta, or rather, here, I'll back up a second. I don't want to skip too many steps. So if we do 16 divided by 8, then we get 2, right? And then we get 2 root 5. So we're going to get 2 root 5 over root 5, not 2 root 5, 2 over root 5 equals cosine of theta. And then we're going to get theta is equal to cosine negative 1, 2 over root 5. And then finally, after doing that, we can get theta equals, let's see, 2 divided by 5 second cosine. I got 26.56. Final answer. And notice that matches our 1 right here. So yeah. So that's how you would do that problem. Are there any questions? The 16 comes from doing this right here. This is the dot product. In order to get the 16, we're going to do 0 times 1. So basically, it's 0 times 1. Yeah. There you go. That's how you get the 16. Any other questions? Yes. Say again. No, this is square root of 5 because we have Oh. Yeah, you can do, are you saying for this right here? Are you saying would you rather have this? It doesn't matter. In most equation sheets, you'll see theta is actually put there, but it could be phi. It's just a variable. Yeah, so like the theta that we're looking for is just, there's no other angle other than the angle like in between these two. So yeah. Yeah. Yeah, I might say phi. You're correct. Yes. Yeah. Just know that whatever angle you're using, that's how you use these formulas. If you put a phi there, just know that you're solving for phi instead of solving for theta. Let's see, we're going to move on. Any other questions though? So let me go over here. You're saying why is it 008? So yeah. There you go. Yeah. Yeah, you're good. Any other questions? Hello, welcome. So now we have another question. It says the position of a particle as a function of time is given by the following formula, and we have this vector function right here. You notice it's a vector because it has the I and the j. At what time t is the particle moving at 45 degrees to both the x and the y axes? So now, okay, we got to actually think about this first. If we want a 45-degree angle between two vectors, right? Now, when we take two vectors, right? Or actually, I'll write this the other way. Now, it doesn't matter the way it doesn't matter which two vectors we have, right? But we want this to be a 45-degree angle right here. Now, notice that in order to make this a 45-degree angle, right? We're going to have A over B. Let's say A over B is equal to C, right? So that means that we need tangent 45 degrees to be equal to A over B, which equals C, right? So if I take this and you do tangent of 45 degrees, take a look what you get. If anybody has a calculator. Basically, if you take tangent of 45 degrees, you get 1, which means that the ratio between these two sides, in order to get a 45-degree angle, needs to be 1, meaning they have to be the same. So A equals B, right? Let's see, I'm going to mute again. Let's go. All right, so yeah, we're going to get 45. We need the same. So it's also asking for the particle moving at 45. No, go back. It's also asking for when the particle is moving at 45 degrees. What does that mean when it says particle moving? What are we looking for? Any velocity. There you go. We're looking for a velocity here. We're not looking for a position. We're looking for a velocity. So this is actually a position function. And if we wrote this as a vector function, it would be 10t. We could say x is equal to 10t squared minus 50. Let's see, now I gotta. And then we could write this as the j would just be 5t cubed. And notice there is no k at all in this problem. Now, what is velocity in calculus terms, what is a velocity in terms of displacement? The derivative. So what we're going to do for this problem is we're going to first find the velocity function by taking the derivative of the x. So we're going to say velocity is equal to, now what's the derivative of 10t squared? And we're doing this with regards to time. So keep that in mind. What is the derivative of 10t squared minus 50 with regards to time? 20t. And that, keep opening that. This button is killing me, guys. All right, so we got 20t. And then we got 5t cubed, right? What is the derivative of that? 15t squared, right? Now, remember, earlier I showed you guys that the two components of the velocity need to be the same in order for the angle to be 45 degrees. So what that means is that we can set these equal to each other to find the time. So we're going to get 15t squared equals 20t. Now, if we solve this real quick algebraically, we can do 15t squared minus 20t equals 0. We get factor out of 5t, we're going to get 3t minus 4 equals 0. Now, obviously, we know that at 0, it's going to be 0, but that's not what it's asking for. It's asking at what time other than 0. This is at 0. So we're going to get a t equals 4/3 seconds, which is equal to 1.23. Okay, so you guys see how that works? Hopefully, it's making a little bit of sense to combine both geometry and calculus basically at the same time to do this problem. Yes. Sure. So like basically it says that there's a 45-degree angle in between the two velocity like vectors. Now, once again, if we wanted to prove it, if we had a triangle right here, this is why I drew this triangle. And it doesn't matter what triangle you have, just make a 45-degree angle. And you have A or B, or you can have any variables you want. Let's say we use C and D this time. Notice that basically when we take tangent of 45 degrees, we're going to get tangent is opposite over adjacent, so C over D, right? Augustus, do you have a calculator on you or no? Do tangent of 45 degrees real quick. Yeah, it just gets 1. So we get 1 equals C over D, which basically means if we like multiply D over, we can get D equals C. So basically both sides have to be the same. Yes.
Tangent of 39 is talking.
See, so like what you could do, right? Let's say it was like, it gave you like a different angle, like it gave you like, I don't know, just like some random like 50 degrees or something. You could do tangent of 50 degrees is equal to this ratio. And then you would still have the ratio of C over D or whatever. And you could plug in that ratio, but you would just have to know that like, if the ratio is like bigger than 1, then that means that C divided by D is going to be obviously bigger or smaller than 1. So you would have to add that constant in to whichever side your C side is. Yeah, you have to find the ratio. In this case, the ratio is 1, yes.
Whatever you fear me more.
Is that Bagman? Let's see. Can confirm that is definitely Bagman. All right. What's up? Sorry. Right. So if it was just like saying like, I don't know, like the particle's position is at a 45-degree angle, then you wouldn't. And if it were to say like the particle's acceleration is at a 45-degree angle, you'd actually have to take 2 derivatives because acceleration is obviously the derivative of velocity. So yeah. All right, so I'm going to move on if that's fine with you guys. I don't want to be here all night, so let's see. All right, so we got another question. We're on slide 6 out of 21. So a car is driven with a distance 8.7 kilometers east, then 4.1 kilometers in the direction 35 degrees north of west. Then the car is driven 7.2 kilometers in a direction 25 degrees south of west. Relative to the starting point, the final location of the car is, all right, this is where I'm going to tell you guys, don't just try doing the math on this problem. It's going to be complicated. What you got to do here is you're going to set up a table. And hope that my pen works. There we go. So we're going to set up a table. We're going to say this is our total X and this is our total Y. Okay, so the first part that we drive is 8.7 kilometers east. Now everything's in kilometers, so realistically the units don't matter. So I'm not going to write the units just for the sake of the room, but technically there are kilometers in the units. But anyways, we're going to have 8.7 here east. So that's like just driving in a straight line that way. And then we have a straight line. So is there any change in Y? No, it's just 0. Now it gets a little more complicated. We drive 4.1 kilometers in a direction that is 35 degrees north of west. So if I draw that, basically we're going to have like, this is like east and west, and this is north and south, right? We're going to go 4.1 kilometers north of west. So we're going to go west, and we're going to go about 35 degrees north of west, and we're going to get something like this, okay? So that's what we drew. So now I'm going to actually put this over here. I'm going to blow it up So basically we have 4.1 and we have a triangle. And right here, this angle is going to be 35 degrees. So now notice that in order to get the y component for this, if we did the trigonometry, if we set this up from geometry, we're going to get the y will be 4.1 sine of 35 degrees, and the x will be 4.1 cosine of 35 degrees. So now if I do that real quick, if I do sine of 35 times 4.1, that is the y. We're going to get 2.35 in the y direction. Now, if I do this 4.1 times 35 cosine, we're going to have 3.35, but there's a slight issue. What is the issue with this 3.35 number? It's negative, right? So technically, you could say that to the west is positive and to the east is negative. You could say that is your point of reference, but typically nobody would do that because it just doesn't make sense. So we're going to say that this is actually going to be negative 3.35. So I'm going to write down the number here. We got 3.35. And actually, no, earlier we defined, because we said this is positive. So yeah, we did define east to be positive earlier. So now we have 3.3585. And this is going to be a negative number. And then finally, I'm going to do the exact same thing for the 7.2 kilometers. The 7.2 kilometers is going to be south of west. So it's going to be kind of like this direction. And it's going to be 25 degrees. And then it's going to be 7.2. So if I do, once again, this is going to be a 7.2 cosine of 25 degrees. And we have 7.2 sine 25 degrees. Okay, if I do that real quick, I got, now notice this is also negative now because it's downwards. I got negative 3.043. And then if I do that right there, we're going to get 7.2 times 25 cosine. And we're going to get, I got 6.525. And once again, this is going to be negative. Tell me if you guys are getting any different numbers, just so that I don't accidentally get the wrong number. But yeah, so now after that, what we're going to have to do, we're going to get our totals, okay? Our total for the total x and the total y. So I'm just going to write here total, because this is like all the times we moved. So now we just have to add them up, each component, and then it'll be pretty easy. So we have that negative 6.5 number, and then we have minus the 3.3585, and we have plus 8.7. And I got a total of negative 1.184. And then after that, we got 2.35 minus 3.043, and I got negative 0.693. So now this is like our total displacement for the two components. So if I just draw this, right, it's going to be something like this, and then it's going to be something like this, right? And this is going to be negative 1.184, and this is going to be negative 0.0693. And we're going to have like a thing right here. And I guess this is the angle we're looking for, right? Or 0.693, my bad, thanks. All right, so then if this is the angle we're looking for, which we could call phi, theta, it doesn't matter. We could say, let's see, we would say tangent, we'll use phi, why not? Equals going to be negative, so it's going to be sine over opposite over adjacent, right? So we're going to say negative 0. It's not 0.069, it's just 0.69, right? Or did let me make sure. Yeah, it's 0.69, my bad, right here. There. So we're going to get negative 0.693 over the negative 1.184. And we're going to get the phi is going to be negative 1 of this number right here. And then if I do that real quick on my calculator, I got 30.34. Degrees. So obviously, once again, this lines up with our number one right there. Any major questions on this question, guys? Once again, I highly recommend if this shows up on the exam to like make a table like this. I know it takes a while for me to explain this stuff, so it might seem like it's like takes forever. But if you're just doing it on an exam, it won't take as long, and it will really help you be more organized, so you can like actually tell what you're doing, and it helps prevent like stupid math mistakes and stuff. Hopefully that makes sense. But yeah, if there's no major questions, I'm going to move on from that one.
Hi, Chris.
Hello, who are you? Sorry, I can't recognize
I'm
you.
leaving. Bye.
Oh, bye. See you.
This is Logan.
Yeah, what's up?
If you go back, when you take the 10 of those values, you get something like 0.01, or did you get something else?
Let me see. So I got 0.693 divided by 1.184. They're both negative. So I got 0.585. And then if I do second tangent, I got 30.34. Yeah. Oh, yeah. Make sure you're in degree mode. Yeah. Okay, so then we have another problem already. So a projectile is launched at an angle 63 degrees from the horizontal. The initial velocity of the projectile is 120 meters per second. You may neglect air resistance. How many seconds after the initial launch does the projectile strike the ground? So for this problem, we're going to want to do some drawing. What does Will always say? What is physics? It's an art class, right? Yeah. So we're going to say a projectile is launched at 63 degrees. I think 63 degrees is like, no, that's not really 63 degrees. 63 degrees is like more upward, right? So then let's just say this is 63 degrees. And then we have like this and this. And it's going to be at a speed of 20 meters per second. Yeah. I switch sides? What? Dude, that's crazy. Okay, hold up. Let me erase this so we don't accidentally mess up this slide. Thank you. There we go. All right, we're going to try this again. So we got 63 degrees. All right, and then we got 120 meters per second. And we're going to neglect air resistance, and it's basically asking how many seconds after the initial launch does the projectile strike the ground. So in order to understand something about this problem, you guys got to know that basically when an object goes up, it's going to, and it's a free fall. When an object goes up, it also takes the same amount of time to go down. So what that means is that if we can find the time that it takes to get to its maximum point, we can just multiply that time by 2 to get the total amount of time it goes up and then comes back down. So if we want to find the time that it takes to get to its maximum point, what are we going to use? What are we going to do? Yeah, did you guys hear what she said? She said we're going to find where the velocity is 0. So also for this question, we only really care about the up and down. We don't care about the x because we're just going up and down from the ground. It's really one-dimensional, but given 2 dimensions. So what we can do is we can say that our upwards velocity is going to be 120 meters per second times sine of 63 degrees, which is equal to 106.92. And what is this actually going to be, like in our physics problem? Like what value is this representing? Initial velocity in the y direction. So now, let me think. We're looking for time. So there's not really a reason for us to use like VF squared equals VI squared plus 2a change in y, because that doesn't give us time. So I think it would be better for us to, let me think. So we need the so the issue is that we don't have the change in distance. We only have the speed. So what if we tried this? Did velocity equals velocity initial plus acceleration times time. Perhaps this would work. Let's see. So we would get the new velocity needs to be 0. And we start off, see how this formula, the reason I picked this one is because the other formulas they use change in y, or they don't have time. So that's neither of the stuff we're looking for. This one, we know we have the initial velocity and we know we have the acceleration because it's just going to be the acceleration of gravity. And we know we have the final velocity, which is going to be 0. So if we use this formula, actually, I think it should get us everything we need. So 0, our initial velocity, I said, is 106.92 meters per second, plus a is going to be negative 9.8. If we define up as positive, which is why this is positive, we need to define down as negative. So that's why the acceleration is negative. And we get time. Well, let me back up. So we're going to get like, when we solve this, we're going to get negative 106.92 meters per second is equal to 9.8 meters per second squared t. The negatives cancel. Now, when I do 106.92 divided by 9.8, we get 10.91. So we have our time is equal to 10.91. But what is this the time for, guys? This is the time to get to the maximum point, right? It's to get to the highest point. And what did I say earlier? In this scenario, we can actually multiply this by 2 to get the time it also takes to go back down. So now if we take this time and we say, I guess like time total or something, this would actually be the time up, something along those lines. So the time total would be 2 times 10.91, which is equal to 21.82 seconds. Final answer matches with the 22 right there. So hopefully that problem, yes. Oh, you're talking about, let's see, you wanted to see this. That was really bad. There you go. That's what that would be, right? Oh, why am I doing everything in the y? Oh, let me, like, I should add, are you saying add that? Yeah. So like, yeah, you could technically, I guess that'd be it. But yes, this would be, basically, if you need to do, you're right. Everything should be in the y direction. Really, the only reason they gave you this 63 degrees and this overall speed, that was purely to mess with you. You really didn't need to know the horizontal speed at all. So keep that in mind. Right. So like if you throw something in the air, you're right. It'll always be like parabolic, meaning that, yeah, you can always just assume that basically the total time is going to be 2 times the time at the highest point. And that includes if you're, that also includes if you're like throwing a football or something. You know, I always joke whenever I'm like playing sports with friends, what, a comp B major that plays sports? That's crazy. I'm always like joking with them. I'm like, dude, you're doing the 2D kinematics in your head when you're throwing that ball. I know you're doing it. This is like actually hacking. I don't know. It's funny. Like I'll play like basketball with my older brother and he's like huge nerd. Like you think I'm a big nerd? No. Wait till you see my older brother. He's a big nerd. But like occasionally he won't even be looking and he'll like throw the basketball and he'll make like, I don't know. Does basketball have 4-pointers? No, it doesn't. But he'll make like a 4-pointer, bro. And I'll just be like, this is insane. What is going on? But it's kind of funny. All right, let's go to the next slide. Okay, you kick a ball from ground level at an angle of 37 degrees to the horizontal and a speed of 20 meters per second. Towards a wall 10 meters away, how far from the base of the wall does the ball hit the wall? So what this is really saying is, okay, so we kick this ball. Why you got to do movement? There we go. So we're kicking this ball and we're kicking it at 20 meters per second. And this is going to be a 37-degree angle. For every exam, every position, sure, yeah, why not? All right. So we got 20 meters per second. I also do this for the discrete exams this semester, if anybody's in discrete. I can post the videos from the discrete next semester, and then you can watch them. But yeah, so we got 20 meters per second, right? 37 degrees. And now we know that this, basically we got this change in X right here is going to be equal to 10 meters. And we got some wall over here, okay? And we're looking for, basically, where does this ball hit? We're looking for a change in Y. When it gets to here, what is the change in Y? So first, what we're going to do is we're going to notice that this is actually a truly two-dimensional problem, unlike the problem we just did, where it was really a one-dimensional problem hidden as a 2D dimensional problem. This is an actual 2D problem. Does anybody know what the one scalar variable in all these equations is? There's one variable in like almost all the kinematics equations that like it's completely scalar. There's no way it changes. Time, yeah, time. You can't really go back in time. I mean, I guess you could say that 5 minutes ago was -5 minutes, but really you don't have the ability to go back in time. So time is always the same no matter what. So given that this question is asking about a change in Y, but it gives us both a change in X and a change in Y, and it also gives us a distance of X meters, I'm going to assume that what we need to do is we need to take the change in X and all those X variables, find the time, and then use the time to find that change in Y. So let's see, if I look at this, we're given a change in X, so we're probably going to use some formula that has change in X in it, and we're given a velocity. Now, we also know the acceleration in the X direction. What is the acceleration in the X direction, given that there's no like air resistance or anything? 0. So there's 0 acceleration. So we also basically have the acceleration in that direction. So now what we're going to do, and this is an initial velocity. Now, first, what we're going to have to do is we're going to have to convert this to X and Y components. So this would be 20 cosine of 37 degrees. And this would be 20 sine of 37 degrees. Also, make sure you always draw the triangle out, but so that you can make sure, but typically Y is just going to be sine and X is just going to be cosine, just so you guys know. Like, it's just usually. Technically, it could be different. So once again, always draw it out, but just usually that's just how it is. So we have 20 cosine of 37 degrees, which I'm going to just do real quick. I got 15.97. So our velocity initial X, I'll write it like this time, is equal to 15.97, 973 meters per second. And we know that our change in X is 10. So now we can probably use this equation right here. Change in X equals VIX T plus 1/2 AX T squared, right? This equation, yeah? Something you guys recognize this equation, hopefully. So we're going to plug in 10 is equal to our initial velocity is going to be 15.973 meters per second times time. Now, once again, what did I say about the acceleration earlier? It's 0, right? So even if we did all the math to figure out these values, what is this entire like part going to be? 0. So we're just going to say plus 0, and basically it's going to get canceled out. So now we can see if we solve for time, we're just going to do 10 divided by that 15 number. So if I do that, I got a 0.626 seconds. Okay, so now we have the time, and what did I say about the time, guys? What can we do when we get the time? We can use it to solve for Y. So we do know the initial Y is this going to be this 20 sine 37. So if I do 37 sine times 20, we're going to get 12.0363 meters per second. And that is the velocity in the initial velocity in the Y direction, right? Now, let me think about this for a second. What do we need? We need to go a certain amount of time. Now, there's really only, I guess we could do this. We could say, and what are we looking for? We're looking for a change in Y. So how can we, what equation has a change in distance and also has a time and an initial and an acceleration? Yeah, it's the same one just for Y now. So we're going to say change in y is equal to, it'll be velocity initial y time plus 1/2 a t squared. And then after that, we're going to say change in y is equal to 12.0363 meters per second times the time, which is 0.626 seconds. And then we're going to get plus 1/2. What's our acceleration, guys? Negative 9.8, yep. Meters per second squared. And then we're going to get our time again, which is 0.626 squared. Now, if I do this on my calculator real quick, 0.626 squared times 9.8, make sure that's negative, times 0.5. And then we're going to add that to 0.626 times. And we got 5.61. So we got a change of y is equal to 5.61 meters per second. Or meters, not meters per second, my bad. Because once again, this is a change in y. And if you looked at the units, the seconds multiplied by seconds cancels, you get just meters. The seconds squared multiplied by seconds squared cancels, you get just meters. So it's actually meters. Yeah. And that's our final answer. Yeah. That's to get, are you saying multiply just this part right here? This part? So that would get you the change in y if there's no acceleration. But you need to keep in mind that there is the acceleration going downwards because of gravity. Yeah. Basically, that's why you notice that if there was no acceleration, right, it makes sense that it would go much further, right, and then the amount of time. But when we include the acceleration, because this is a negative 9.8, it actually makes it lower. Yeah. Yes.
Well, why is acceleration only in the y? Why is there
So basically, when we're looking at the acceleration for different components, or and this goes for anything, velocity, acceleration, it doesn't matter. They're completely independent of each other. So if I throw a ball up, the speed it's going this way and the speed it's going up and down, they are completely different. Like they're separate. You treat them separately. So when I'm using an equation in the y direction or in the y-axis, y dimension, whatever you want to call it, all of your variables are going to be completely different from your variables in the x direction. And that's just why we are doing it specifically for like x and y. You'll see in this equation, the only thing that's shared once again is time, which is the same in both directions basically. But notice that in both equations, we're using only x variables or only y variables. We're never combining the two. Of course, yes.
How do we think about it if the ball had never reached the wall?
Oh, if the ball had never reached the wall. So basically what we would be doing then, right? Let me think about that. If the ball had never reached the wall, basically what that would give us is we would end up getting a negative answer. If we did this problem and the ball never reached the wall, we would get a negative answer, I think, because that means it would basically go up and then it would make the parabola and then it would basically be as if it hit the ground before, but we don't know the ground exists in the math. So it'd be as if it's going underground. So that's how you know the ball doesn't hit the wall if you get a negative answer. In which case, this change of x would just be straight up wrong. You'd probably get a different question like, what is the change of x if you just throw a ball? And that's what I could see happening. Yes. Say it again one more time. Sorry, I just couldn't hear you. Yeah, so like, yeah, you're correct. Unless you have like, I don't know, like a motor on your ball that's like pushing it forward or something. But yeah, it's always zero for the most part. Maybe we could get some like crazy question where it's like we like put a jetpack on our ball and it starts accelerating this amount forward. But in that case, I think we'll be given the acceleration. What's up? Okay, if I throw, what's something I can throw? A pen, right? If I throw this pen, okay. Notice that basically, if there was no air resistance or anything, right? It's pen, if there was zero air resistance, and theoretically, and assuming it doesn't hit the ground or anything, it would theoretically just continue going. Like if I were to go into space into a vacuum, right, and I threw this pen, it would not stop. It would literally just keep going. The only reason it stops in real life is because you have stuff like drag force and air resistance. So it's basically friction that's force. There's a small force of friction that's pushing it back eventually, and then it eventually stops. But basically, if that wasn't, all these problems were assuming there's no friction or anything. So if that was non-existent, it would just keep going because there is zero acceleration. There's nothing like pushing it back. It's just Newton. That is actually the definition of Newton's first law. If you're going at a specific velocity and you have no force, no acceleration, then you just keep going. Yeah. So it kind of answered the question, hopefully. Okay, cool. Any other questions? Okay, cool. We'll move on. Let's see. Where's my mouse? Come on. Gotcha. Found it. All right. Next question. Oh, this question is actually, it's pretty easy, but the thing is, the way that they ask this, the wording is like so goofy. So like, that's why I wanted to go over this one, because I noticed that there was a question similar to this on literally every single previous exam, just so you guys know. So like, pay attention. The wording on this question is so bad, honestly, in my opinion, but I will explain what the wording means. So it says a 120-meter wide river flows from south to north at a speed of 0.3 meters per second. South to north means it's going up. No, I went back. South to north at 0.3 meters per second. Now, Tarzana, don't know if I pronounced that correctly, but Tarzana is swimming at a speed of 0.5 meters per second relative to the water. Now, when it says relative to the water, when I first did this problem, I looked at this graph right here. I thought, okay, Tarzana is swimming this way. That means that obviously her speed is 0.5 meters per second, right? No, that's not what the questions say. It cannot be that simple. What this actually means is that Tarzana, she's moving straight that way, right? But keep in mind, to move straight that way, what that actually means is that you're partially swimming down in order to cancel out the upwards motion of the water. So Tarzana is moving that way, but she's actually swimming, her velocity is that way. So now that we know that, we have 0.5 meters per second in that direction. And now what we're doing is we're trying to figure out the total time it takes to go this 120-meter distance. So once again, we cannot do stuff in separate dimensions. So what are we going to have to do here to find this? Any guesses? So what I'm going to do, you guys like remember all the way back from geometry? Like, I don't know, some of you guys are pretty old, let's say like 10 years ago. Okay. You remember all the way back from geometry when you learned like what a 3-4-5 triangle is? This is just a 3-4-5 triangle, but instead of 3-4-5, it's 0.3, 0.4, 0.5. So we know that this is actually 0.4 meters per second in that direction. Now, once again, let's look at our units real quick. What are we looking for? We're looking for time, right? So if we have 120 meters and we're moving in that direction at 0.4 meters per second, how are we going to find the time? Well, what do we do? Look at the units. All right, see ya. Basically, what we need to do is we got to divide 120 meters divided by 0.4 meters per second. And this is going to cancel, this is going to cancel. And then this first second is actually going to go up. And then we're going to get, we do 120 divided by 0.4. We get 300 seconds. And that is our answer for this question. Do you guys see what I did there with the units? That's what you have to do for like a lot of problems, Loki. You got to look at the units and just like kind of figure it out. Hopefully that makes sense. Okay, yeah, I can explain it again. Did you see how I got this number right here, the 0.4? Okay. So basically what I was saying is we have in the dimension that we're trying to figure out, we have that we're moving 0.4 meters per second and we're going 120 meters. So I was just saying in order to get the time, when we have a meters and a meters per second, we have to go, if you think about it, if we do meters over meters per second, right? This is the same thing as meters. And we'll just say this over 1 times second meters, because we like do the inverse or whatever. Inverse, reciprocal, something like that. I think reciprocal is the technical term. This cancels out and we just get seconds. So that's why I'm basically taking this 120 and dividing by the 0.4. Yes. Yeah, you would just use Pythag, yeah. So basically, once again, this is the worst wording I've ever seen, to be honest, but I know this is going to show up, so that's why I'm going over it with you guys. But basically, when it says right here, when it says 0.5 relative to the water, what it actually is saying is the way she's moving is just from here to here, basically. But in order to just move in a straight line, when you have this 3 meters per second going up, it means that she actually has to be, like her direction is actually slightly downward in order to cancel that out, basically. Like she starts at point A and she ends at point B. This is how she ends. But since this is going up, it means that she actually has to partially be swimming downward in order to end at the same point. It's kind of like if you're at the beach, if you go to the beach, you go into the water and then like you mess around on the beach for like, I don't know, let's say you mess around for like 20 minutes. And then you all of a sudden, like, I don't know, you went out and you went like directly in front of like, I don't know, wherever you set up your, like your beach chair and stuff, right? And then 20 minutes later, you realize that you're like really far out from the beach chair and you're just like, what the heck, man? It's like that. It's doing that, but in a physics problem. And it's basically canceling that out so you're still right there in front of your beach chair.
You should go from point A.
Yeah. Yes.
I will, it's like 11, 12, 13 or.
5, 12, 13, I think. Let's see, 5 squared plus 12 squared equals 169 square root 13. Yeah, it's 5, 12, 13. Obviously, if you didn't know them off the top of your head, then you do it on a calculator, you're still going to get the same answer, so you don't have to actually have them memorized. Okay, ooh, this is a really good problem, and this is another one, once again, that I noticed showed up on every single exam, so like, pay attention. So basically how this one works is we have a force, and then we have 2 blocks. And I think after this question, I also have a follow-up question that is like a similar concept to this question. We have a force and we have 2 blocks, and we have this force going on the right of the 2 blocks. So now, when I first looked at this question, I was sitting there like, okay, what's the difference between these 2 blocks? And the first thing I thought of was, okay, obviously one of the blocks is bigger than the other block. But after looking at these equations and figuring it out, I realized that's not actually what matters. It does not matter which block is bigger than the other block. It matters which block is on the side that the force is happening on. The force that little m puts on big M is equal to the force that big M puts on little m. No, this is not a discrete implication. This is just an arrow. But anyways, this is just an arrow. Now, those forces are equal. So it doesn't matter. It shouldn't matter like, what did I just do? It should not matter. Or what the heck did I do? This is crazy. I like made it like different, but okay. Maybe, how do I turn it off? I don't even know. Oh, it is what it is. So what we're going to do is we're going to say that what is the total force here, guys? What is the total force equal to? The force that this puts on these blocks. Well, we're going to be looking for the magnitude of the force. So what is force usually? MA, right? So if we look at the total force, what is this going to be? So what's the M first?
Will it be little m plus big M times acceleration?
Now, let me tell you something, right? This acceleration, the net acceleration, right? Isn't this going to be the same for both blocks? Because this is the same because they're connected and they're moving together. So aren't both blocks like the acceleration that is the net acceleration and the acceleration of like just the block on the left, smaller block, aren't they going to be the same? So couldn't you say that if you found the force in just the block on the left, it's still going to have the same acceleration because it's still moving the same way. It's just a different piece of that block. You guys understand that logic here? So now, let's say we wanted to find the force that basically just is between these two blocks, okay? Which I already established is kind of equal. What would that be? What is the small block pushing on the big block? How much force is it? I'm just going to call this force between, or just force B. It's not the net force, just to make that clear. So what would this be? Well, how much mass does the small block have? Little m. Yeah, I don't know how to, oh wait, I found it, it's right here, crazy, okay. So there's a little m, right? And then we have A. And isn't this A the same thing as A net? Because it's the same acceleration, right? So we have A net. So now what are we going to do here? We're looking for this in terms, this net force that's in all the answers is the net force. So we're looking for this, but instead of in terms of A net, we're looking for this in terms of the net force. So what are we going to do? So if we solve for this, yeah, we're going to get F net over m plus m, right? And then if we go here, we're going to say the force between them is equal to our little m is still there, and we have our F net. We plug this in for the acceleration, and we get this over m plus big M. And notice that is our answer. Now, this question, yes. If we for which part? Like this right here is the smaller mass. Like, are you saying what if we did this? So here's the thing, right? I don't want you guys to think about this really as the small block on the big block. I want you guys to think about this as the left block on the right block. It doesn't matter which one's smaller or bigger. It matters which one is close to this force and which one is not. Does that make sense, guys? Like this small M and this big M in this example, they are like how they denote them. Yes. If there's friction, so basically, that is, well, okay, think about this. What? No, the next question has to do with tension. But if there was friction, right? How we would find the total frictional force between these two? If we would find like the force of static friction, it would still be U static, and then the normal force, right? Now, if you wanted to find the friction of just the smaller block, then remember the normal force for just the smaller block would be mg. If you wanted to find the total friction for like everything, it would be m plus. Well, here's the thing. It doesn't matter for like the force between the two, but if you have friction and you're solving for something else, like basically if you're solving for something else that you maybe you're trying to like solve for like a speed or a time or something, then you might have to figure out, but then you'll be given that information probably like extra, unless it's like one of those questions like our quizzes where it's like we're given a million variables. Like you wouldn't have to solve for that though in a contact question most likely, because the friction, since they're basically connected, would just be kind of the same for both of them. With that being said, I do want to go to a tension question, and we do have plenty of static friction questions coming up. So, yeah. Yeah, so here is a question. This is the same concept, just with ropes. And notice that when you have a ropes, you're typically not pushing, you're pulling, but it's still the force is over here. So it's basically saying, what is the force in this rope? Okay. How do we find the force in this rope? Well, let's go back a slide. Let's do exactly what we did here, and we're going to do it here. So the total force, now notice that each of these has a mass of m. So I'm going to replace this with m, m, m. They're all the same mass. So the total force is going to be F equals, what's the total mass, guys? 3m. This will be the net force. It's going to be 3m, and then acceleration. And once again, it's all going to be the same acceleration because they're connected, right? So I'm just going to call this acceleration net. So then after that, we have, we're looking for the force of tension in this rope. So I'll just call force of tension. And if you wanted to be specific, it would be the force of tension between B and C. Well, what this is going to be is, notice that now we have A and B, right? Like the only two masses that this is pulling is the mass of A and B. So what would the total mass between those two be? 2m. So now we have 2m A net. Right? Now we're going to do the exact same thing we did with the last problem. We're going to say A net is equal to F net over 3m, right? And then we're going to plug that into A net. We get F tension between B and C is equal to 2m, and then we get F net over 3m. We cancel out these m's because they're on both the top and the bottom. Basically, we get 2f over 3, which right here is our answer. You guys see how that is the same exact thing applied in a different way. So hopefully that makes sense. I wanted to show both of those scenarios so that you guys can see how you take one concept and apply it to a problem just a little bit different. Yes. That's the force of tension in the rope that is between B and C. Let's see. So if we move on from here, also, I just realized I haven't been paying attention to the Zoom chat at all. I'm so sorry, guys. This is like tragic. There are so many questions in the Zoom chat. I'm just looking at what it's saying. Somebody said, what is Pythagorean theorem? Well, I have unfortunate news to tell you. You might want to go back and review that. Somebody said, hey, Crystal. Cosine and not sine. That would be, I'm assuming you were talking about like one of these questions, like here. Just keep in mind that if you write out, it's like sine is equal to, opposite over adjacent or opposite over hypotenuse. So it'd be like here, here. That's how you do sine and cosine. It's just you just have to look. Yes.
The angle, like the cross product is sine.
For a cross product, you use sine. And also, if you're doing the cross product, you need to make sure to take the magnitude of it. Yeah. And then dot product, you use cosine. All right. And let me see if there are any more important questions. Oh, that question for cosine and sine was actually just about that for like stuff. We have somebody, a certain individual talking about his life. Somebody's phone died. It's tragic. On this question, you took into account both masses when doing the tension, but the other question before you did just one of the m's. That was because in this question, we had a total of 3 masses, and there were 2 masses on the left. In this question, we only had 2 masses, and so there was only 1 mass on the left. If that makes sense. They are connected in this question, whereas in the previous question, like in this question, we were talking about between here, and you can see that between here, there's only 1 thing on the left, so that's all we were looking at. In this question we were talking about here, you can see there are 2 on the left. Yeah, hopefully that makes sense. Yeah, what's up? What? We're on 12 out of 21. Yeah, sorry. I know it's taken a long time, but like it just kind of is what it is. 8:20. All right, of course. So yeah, so somebody said it's just whatever's to the left of the force. So like once again, it's basically you're looking at, what are we looking at? We're looking at the force here. And when the force is on the right, so we're looking at the left. Now, if the force was on the right or on the left, we'd be looking at what's at the right. Okay. So now, okay, this question, I'm not 100% sure if a question like this can show up on the exam or not. Like we kind of went over pulleys, but like we kind of didn't. But I want to go over this anyways. So yeah. Okay. Yeah, like I just wanted to go over it to make sure. So we have this pulley system. Now, what you guys want to understand about pulleys We didn't really go over this honestly too well in class. When we go over the pulleys, it doesn't matter when the pulley changes direction. Our dimension for a pulley literally warps with the pulley itself. So a pulley is usually going to be a one-dimensional problem, actually, even though it's multiple dimensions. What that means, when we define our x and y axis or our positive and negative, it's going to be this way is positive, and this way, well, if I guess that's the same color, but this way is negative, or vice versa. It doesn't matter, whichever one you want to define as positive and negative. It doesn't have to be like up and down is positive and negative and left and right. It's literally just if the pulley is, what did I do this time? Cool. It's literally just if the pulley is going this way on the pulley, it can be positive, and if it can go this way on the pulley, it's negative. Treat it as a one-dimensional problem. So if we're going to treat this as a one-dimensional problem, well, we know that block B, which is pointing down, which is this way on the pulley, notice it is, I keep pressing a button, but it's this way on the pulley basically, right? So which direction do we want to be positive or negative? Let's see, let's think about this. We'll just make B's direction be negative, and we'll say that this is going to be negative 11 newtons, okay? Now what we're also going to do is we're going to take it, now we can see that there's a rate of 22 newtons on this block. So now what are we going to have to do? Which direction are we concerned with? This 22 newtons is pointing down, right? But we're really only concerned, once again, we're going to make this into a one-dimensional problem. What are we concerned with? So if we make this into some form of right triangle, right? We could make this into a triangle like this, and that was a terrible drawing. We make this into some form of right triangle. Say it's going to be like something like that, right? Well, this is for the force of gravity. Yeah, sorry. So this is our force of gravity, which is 22 newtons, right? Which dimension are we concerned with, guys? If earlier I defined basically the pulley being our direction, which direction are we concerned with? Any guesses? Are we doing this one right here or this one right here? Yeah, this top direction, right? Sorry, that was not very clear, but basically, we're gonna concern ourselves with this direction. So now let's read the question. It says both blocks are stationary. Now, what does stationary mean? It means that the net force is going to be zero, right? The net force of our pulley is zero, which means that this 11 newtons is going to cancel out with whichever component this side of newtons of this block, which is the force of gravity. So we're going to say something is equal to 11 newtons. Now, what's that something? We have our force of gravity, which is equal to 22 newtons. And let me remake that triangle right here. 22 newtons. And we're looking for basically right here. Let's just label that A. Now, we know that this theta right here is 33 degrees. So now if we have this triangle, right? And this is 33 degrees. What is this angle right here? Now notice, this angle right here is the same thing as this angle right here. And that angle right there is the same thing as this angle right here. And if we have a 90 minus, now this angle right here is going to be 90 minus 30, right? 33 actually. Now, what does that mean? It means that this angle right here is just our original 33 degrees. Do you guys see that, like geometrically? Our 33 degrees from the incline, if we look at our force of gravity, is also right there, because it's this angle really that we're looking at, and then you can do another 90-degree triangle, and you see that our force of 33 degrees is right there. So this means that if we're looking for A, and we're trying to find, and we have the hypotenuse, which is the 22 newtons, what's trigonometry function would we be using? Sine? You guys in agreement with sine? Okay. So we're going to say force of gravity in the, I don't know, what do you want to call this? The pulley direction, I guess. The pulley direction is going to be 22. Slope direction, pulley direction, doesn't really matter. We're going to say 22 newtons sine of 33 degrees. Okay, which is equal to, if I do that real quick, times 22. I got 11.98. So 11.982 newtons. Okay. So now we have, and now what is it actually asking for? It's asking for what is the magnitude of the friction force. Now notice, we're going to have two forces on this block in this direction. We're going to have the force that is the gravitational force, and then we're going to have the frictional force. So what this really means is what is equal to this 11 newtons? It's going to be the force of the gravity in the forward direction plus the force of, what do we want to call it? Static force in the forward direction is equal to 11 newtons. So that means is that, or rather, let me take that back. So what we have here, it's actually slightly messed up. If we have this 11 newtons here, right, then we know that this plus the frictional force actually, the static friction force is actually stopping movement. So we have this plus the static friction force of the pulley is equal to the force of the gravity of the pulley. Because since the gravity is pulling this netwards down, you can see that the gravity is greater than this force. That means that the frictional force is actually going against that movement and going that way. So that's why the frictional force is the same direction as the force of block B. So if I finally plug in our numbers, we're going to 11.982 newtons is equal to 11 newtons plus the static friction pulley force direction, whatever you want to call it. And then we're going to get this is equal to 11.98 newtons minus 11 newtons equals 0.98 newtons. So hopefully that kind of makes sense too. Once again, friction, it always opposes to like movement. So friction is never a specific direction. It's when you solve for everything and you see what direction it's supposed to be moving. Without friction, friction is going the opposite direction. So keep that in mind. Also, this is a really bad end, so I'll fix that real quick. Once again, I don't know if this will be on the exam or not, but I just want to go over it just in case. Okay, this question is really easy, guys. But then when I actually thought about this question, I thought about it, I was like, wait a second. They could make this exact same question a trick question. And so I wanted to go over this question, not just to go over the question, but to go over how they could make this a trick question, okay? That way, in the case that we see this question on the exam, we already know the trick. We don't even have to think about it. So here's the thing, right? It's saying that a force is being applied to this block, right? And the block is sitting on the wall, and the block has a mass of 1.5 kilograms, and it's just sitting on the wall, right? Now, if we make the assumption that we are putting enough force on the block so that it's not moving, if the block is not moving, what's the net force on the block? Yeah, it's zero. It's right here. It makes sense, right? Net force is zero. That's the answer, because the block is not moving. But what I came to the realization while looking at this problem again, I realized, okay, what if the force that we are putting is 31 newtons? What if this force was less than basically was less than the force, or rather, the force that this is going to cause to be static friction? What if this was less than the force of gravity? Well, that makes an issue. Now, I'll show you in a second. Yeah, don't worry. I plan to do this. So here's the issue, right? We know that this is 1.5 kilograms. So that means that the gravity is going to be 1.5, not grams, 1.5 kilograms. And we have 9.8 meters per second squared. So we know that the force of gravity on this block is equal to, if I do 1.5 times 9.8, we have 14.7 newtons. Now, what is the force of static friction? Once again, or rather, which way would this thing be pointing? Which way is static friction pointing? Up, yeah, because our gravity is trying to go this way. And that means that our force of static friction must be trying to go this way, right? Now we can find our force of static friction. And if we use this equation right here, do you guys remember learning this one? Force of static friction is the coefficient of static friction times the normal force. Now, if we use this equation right here, what does it give us? It gives us, that actually does not give us the current static friction. That gives us the maximum static friction. The real formula is not equals to, it's actually static friction is less than or equal to US Fn. That's the real formula. So this is actually, this formula right here is giving us a maximum, okay? It's giving a maximum static friction that can occur. So if we put that right here, and we say we're going to solve this. Now, what's the normal force? Do you guys know? Remember that this force, we're pushing it into the wall. What is this wall right here? Do you guys notice that's a flat surface? What is normal force? It's when you push on a flat surface. And notice if I push on this table, well, actually the table's wobbling a little bit, but if I push on this table, my hand's not just going through the table, right? That's a normal force. If I push on this wall, I don't know, I'm not going to touch the whiteboard with my oily hands, but if I push on this wall right here, I'm not going through the wall. There's a normal force being applied to my hand that's basically going that way. And it's the opposite of the force that I'm pushing this way. That is a normal force. So our normal force for this problem is going to be the same 31 newtons, or at least the magnitude is going to be the same. It would technically be a different sign, but the magnitude is going to be that 31 newtons. And we have that 0.6 as our static coefficient of friction. So we have our force of static friction is equal to 0.6, 31 newtons, which is going to be 18.6. Now notice this 18.6 number is our maximum force of static friction upward, and that is greater than our force of gravity going downward, which means that yes, this square, this box, whatever you want to call it, is going to be in place because the force of static friction is high enough to keep it in place. But now what I want us to keep in mind is that, let's say theoretically, right, this right here was like, let's say we had a greater mass. Let's say we made it like 4.5, okay? 9.8. Let's say that would just be that times 3, right? So we get 44.1 newtons. We would get 44.1 newtons. And then if we subtracted our maximum force of static friction, what we get is this. 44.1 minus 18.6. What we get, our net force in that direction is actually 25.5 newtons downward. So then our net force would actually be a real number. And what that would mean is that we don't have enough static friction to hold that onto the wall. So yes, the box is falling. The box is not still. So that's what I wanted to go over with you guys was I noticed, like when I first looked at this problem, I just saw it was 0 and I was like, okay, it's obviously 0 because the box is in a standstill position. That's what I'm assuming. But what if I didn't assume that? What if I couldn't? That's what we'd actually have to do to check. We'd have to make sure that the static friction is greater than or equal to the force of gravitation. Yes.
So if there is no friction on the wall, it doesn't matter how hard you press the block, it's still going to fall.
Correct. If the coefficient of friction was 0, it wouldn't matter. You're right. It would fall no matter what. Yes. Yeah, you cannot assume actually. Now, once again, when I first did this problem, I assumed it was 0 and I happened to get the right answer because I made that assumption. But then I thought about it later and I was like, dude, if I did this on an exam, theoretically, they could give me like a greater mass and that assumption would be incorrect. So that's why I like this, like almost tripped me up basically. Yeah. So hopefully that makes sense to you guys. Yeah, what's up? So the 4.5 was just giving an example, like what if the mass was 4.5 instead of 1.5? And in that case, you would see because it's a greater mass, the force of gravity would be greater than the force of the maximum force of static friction upwards, which would mean it would actually be falling down, and we would have a net force. Yeah. Yeah. See, my understanding, and this could be incorrect, but my understanding is the reason they gave you the coefficient of static friction and the mass is because they don't want you to assume that. When it says pressed against the wall, I mean, I guess they're thinking technically it could still be moving, but I don't know, like in my opinion, that would be a trick question. You know what I mean? Like realistically, that would be a trick question if it actually were moving. But at the same time, that's the type of question I could see being on the exam. So yeah. All right, so then we have, oh, this is a pretty easy one if you know calculus, which I think everyone in here is taking Calc 1, right? Like it's like a prereq for the class. So if you've taken calculus, this is really not a hard question. You just need to know what's going on. The biggest thing with this question is actually looking at this graph and seeing, you see force. Now, if I tell you to take the derivative of force or the integral of force, some people are like, what the heck is that? But let's actually think about this for a second. What is force equal to, guys? What's our equation for force usually? Now, if we have mass times acceleration, isn't the mass usually constant? Like you're not gonna like randomly, I don't know, gain weight in the middle of like, I mean, maybe you could, but I don't think anybody's metabolism is that slow, right? You wouldn't just randomly gain weight. So really, what is this mass number? Isn't that just a constant? Like, so if you look at a force graph versus time, you really just have a constant times acceleration. So isn't this actually just the same as looking at an acceleration graph? If you really think about it, like conceptually, it's just looking at an acceleration graph multiplied by a constant. So what that means is if we take the integral, now remember, take the integral, it's backwards of the derivative. Take the derivative, you're taking the rate of change of something. So if you take the derivative of position, you're all of a sudden you're going from meters to meters per second. You take the derivative of velocity, you're going from meters per second to meters per second squared. You take the derivative of acceleration, I think that's like jerk, something like that. You're going from meters per second squared to meters per second cubed, etc. Now doing the derivative or the integral is the exact opposite. You take the integral of acceleration, you're going to velocity. You're going from meters per second squared to meters per second. Take the integral of velocity, you're going to position, meters per second to meters. You can do this exact same thing with stuff besides displacement, velocity, and acceleration. You can also do this with like, if you have like, and I will tell you, we will learn this later in the semester 100%. Power is the equation for joules energy per second. So that means that power is really the derivative of energy. No, work is energy, but power is energy per time. So, you know, power supplies, PC building, this goes into that. But, so yeah, when we do power later, you'll see that we can take integrals of power to find work or energy, whichever one you want to call it. But for this question, we're looking for when is the velocity 0, and we have an acceleration graph. So, well, we have a force graph, but once again, force is basically the same thing as acceleration, just multiplied by a constant. So, what do we do to find when the velocity is 0? What if we look at this graph? And also, I'm going to highlight this. This is 0 right here. This is the axes. We're going to take the integral, because to go from acceleration to velocity, we take an integral. And we're going to look at what does an integral actually mean. If you take an integral of like a function, yeah, an integral of this function would be this area, right? So what would that mean then? If the integral needs to be 0, the integral of acceleration needs to be 0, and we look at this graph, what does that mean? Yeah, the net area needs to be 0. So if we look at this right here, we first start by having a positive, and then we go into the negative, so we start subtracting, and notice that they cancel out right at this point here, which is 4, which is our answer. And that's the only time they cancel out in that graph. So hopefully that makes sense. And hopefully you can use this not only to apply it to, you know, position and velocity and acceleration, but hopefully when we get into later things in the class, we can apply the same logic there as well. Okay, so this one's also completely conceptual. You stand on a bathroom scale and it reads 50 kilograms. You take it into an elevator. I don't know what you're doing going into an elevator with a bathroom scale, to be honest, but you take it into an elevator and at one instant it reads 60 kilograms. What can you deduce about the directions of the elevator's velocity and acceleration at that instant? Well, we know that the truth is your force is staying the same, right? You still weigh the same on the elevator. What's really changing is this is actually relative acceleration. We know that force is equal to mass times acceleration. Does our acceleration tell us anything about our velocity, really? Does it tell us what our velocity actually is? What does acceleration actually tell us? It tells us how our velocity is changing. Once again, it's the derivative of acceleration or of velocity. So it tells us how our velocity is changing, but it doesn't tell us our actual velocity. We know nothing about that from this formula. If I tell you you are accelerating at 5 meters per second squared, you could be moving at 3 meters per second, or you could be moving at negative 1,000 meters per second, and you could still be accelerating at 5 meters per second squared. We don't know our velocity. So if we look at this question and we say that our weight normally, normally it's 50 kilograms. And now all of a sudden it's 60 kilograms. Well, think about it. What do we need in order for that to happen? We need we know that this is the same. And now, but now this has gone from a lower number. If I erase this to a higher number, we've gone from a lower force to a higher force. Our mass is still the same. What happens to the acceleration? It goes up as well. They're proportional. So that is why, once again, we don't know anything about the velocity because we really don't, but we know the acceleration is up. No, because think about it, right? Let's say we had a positive, say we had a negative velocity. We had negative 300 meters per second, right? And let's say our acceleration was 5 meters per second squared. Okay, what does that actually mean? What are we doing? Are we slowing up or speeding down? We're actually slowing down. We're actually slowing down because it would be like let's say this was negative and this was positive. If I was moving this way, well, I'd be really, really fast. I'd be like as fast as a flash if I was running this way. It means I'm running really, really fast, but my acceleration is that way. So I'm basically running really, really fast and slowing down. However, with that being said, we could also say that maybe I'm running 10 meters per second with the same acceleration, right? I could be running this way, maybe a slightly more humane pace. I could be running this way, and if I'm speeding up at 5 meters per second, it means I'm speeding up that way. So literally the acceleration tells us nothing about the instantaneous velocity. It tells us whether we're speeding up or slowing down, depending on it, but it doesn't tell us anything like direct about the actual number. It could be either positive or negative. When a car mass 1,200 kilograms going with a speed 30 meters per second rounds an unbanked curve of radius 150 meters, what is the minimum coefficient of static friction needed to ensure that it does not skid? Okay, so the first thing I'm going to think about here, we have a static friction coefficient. We have a mass, we have a speed. We also see unbanked curve. Now this should be a huge, look at this, guys. When we have an unbanked curve, it means you need to think of circular motion, most likely. Now notice we also have a radius there, which once again, it also sounds like circular motion. And we also have a speed. Now, what we need to know is that the acceleration, or rather the force of centripetal, is going to be equal to the net force, right? When you're doing centripetal acceleration. But let me see minimum. So we're looking for the force of static friction, and this is unbanked, so there's no force like gravity or anything like messing with this. There's no angle that we have multiple forces with. So we're going to say the force of centripetal acceleration is equal to the force, let's just say static friction, right? Now, what we're going to do here, we're going to see that we have 30 meters per second. Now, here's the thing, right? If we expand these, first we're going to do this. I'm going to say mass, or rather, yeah, mass times AC is equal to the coefficient, why did I say kinetic friction? I meant static friction times the normal force, remember that? So now we get M AC is equal to the coefficient of static friction times what's the normal force when it's like just something flat? Like we don't have to worry about any fancy angles or anything. Just mg? Yeah, sounds good to me. So we're going to say this is, now notice something kind of interesting here, right? Notice that there's two m's. What does that mean? Cancel out. There's two m's and they cancel out. Well, we'll see in a second if I get this correct, but if there's two m's in the answer, cancel out. Do we really need this 1,200 kilograms here? I guess not. Cool. So we're going to say AC equals US times G. Now what's AC equal to? V squared over R equals USG. Now that means a US, and I say U, but it's actually like a mu or something, right? It's like a Greek symbol. Mu, I don't know. We could say like mu, like the Pokemon or something. So we get V squared over R times G, which is going to be that 30 meters per second squared over, and the R is going to be 150 meters times gravity 9.8 meters per second squared. Let's see if our units work out, right? What do we need? We need no units actually. So on top, this is going to be meters squared per second squared. On bottom, this is also going to be meters squared per second squared. So then we're going to get no units, which sounds correct. Let's see if I solve this, if I get the correct answer of 0.61. Got 0.6122. There you go, answer. Cool. So that's how you do that problem. So really, what is this 1,200 kilograms here for? It's, yes. Wait, say again, sorry. How did I set it? It's C to add to S. So like, because it says that is given by, it is an unbanked curve, right? Now, when you have even a banked curve, the centripetal force is always equal to the net force. So basically what we have here is we just have like a straight circle, like there's no other dimensions. If we looked at this from like the side, I guess it would look something like this, like a racetrack type thing. And we're just going around and it's flat. So basically what we know is the only force when you're like driving a car or something, when you're going around a flat surface, is basically going to be, there's going to be gravity pointing down and normal force pointing up. But those are going to cancel each other out. So then the only force that's like going to be like actually present is going to be the force of friction between like your wheels and the ground. Like there's no other force that's going to be there. So if this were like a banked curve or something, where this was like, I don't know, a funnel, I don't know, like there's like an angle or something, then it would be a little bit more complicated because we would have to like do some trigonometry to figure out the angles and all that. But I can guarantee you, or at least I hope not, that we won't get a question that complicated on the exam. So yeah, but basically that is why, because I know that the actual, like the total amount of force is really just the force of friction. That's all that there is. That's how I know to set this net force, which is the centripetal force, equal to the force of static friction. Yes.
On a flat surface is always equal to the normal force.
The force of friction on a flat surface is equal to the normal force times the coefficient of friction. Now, something interesting, right? This is a car. Car right here. You see that? Now, how do you guys think a car moves? Well, you're great. When you look at a car, Oh gosh, how do we draw a car, guys? All right, let's see. Maybe we can try this. All right, good enough. We got like a V8 in here, guys. It's like a little bit large. Okay. V10, you know? Okay. So basically, when we look at a car, how do you guys think a car is actually moving? Is it sliding? No, the wheel is moving. So believe it or not, if you're skidding in a car, you are sliding. Therefore, you're using the coefficient of kinetic friction. But if you're just moving in a car normally, what's actually moving you is the force of static friction, just so you guys know. So if we said like a block was sliding around a track, like maybe an ice track or something somehow, if it says a block was sliding around, then it would be kinetic friction. But because it says it's a car is using static friction. Yes. No, not to my knowledge. I think they have to both be given to you separately. After this one, well, on 17 out of 21. Yeah, we're slowly making progress. Yes. So yeah, in the ice block example, because it's actually sliding, like we wouldn't be using static friction at all. We would be using kinetic friction, to my knowledge. And I think like the only way you'd be able to do that, by the way, is like if there were a problem and it was like you have a block connected to a rope that is then going around, I don't know, around a ice rink or something, like it wouldn't make sense otherwise. Because if you just slide a block, it's just going to go one direction, right? So you have to have something that's also forcing the acceleration there. In that case, it would be tension. Okay, this problem right here. A car travels over a hill of radius 60 meters. Once again, we see that key word right there, radius. What does that mean? What are we probably going to do? Yes. So, everything. So basically, we would have this, right? And we know that the acceleration, the centripetal acceleration would be that way, right? And it's going around. So I guess realistically, if we're setting these equal to each other, then I guess this would be turning. So I think it's more the static friction is the entire component of the centripetal acceleration. So I believe it would be pointing in the same direction. I could be wrong with that though. I would like Google it to make sure. But I believe if you were setting this up as a force body diagram, it'd be the same thing like if I had like a force like this, right? And like it's like 3 newtons. And then like we're also applying another force of like 5 newtons. Like these two forces would be 1 8-newton force, like in the same direction type thing. I think that's how this works too. Because once again, you might have another force here and that are all adding to be the force of centripetal acceleration. If it's like a banked where it's like an angle and you have another, force acting upon it. That makes sense. But once again, Google that to make sure. Let's see. Okay, cool. So let's see, a car travels over a hill of radius 60 meters. Once again, that is a key word that we're probably going to be using some form of uniform circular motion here. You can also see the picture. You can already see a circle being made, right? Right here. What is the maximum speed that it can travel without it losing contact with the road at the top of the hill? Okay, so it's at the top of the hill, so we're going to say it's right here. Now, what forces are acting on the car when it's right there? Gravity. So gravity is going to go down, right? So let's say that basically our what other type of force is going down right now? If this is a circular motion problem, centripetal acceleration. Say again, sorry. Oh, what? Maybe I just. Okay, are you talking on purpose or no? I'm just going to assume not. All right. So basically, what we're going to have here is yes. Yes, this is a centripetal acceleration with hills, but we need to keep in mind now that we're doing this centripetal acceleration, and basically, if we look at this gravity, where is this gravity pointing? Downwards, right? So what this means is that, and how many forces are acting upon this object? Now, remember, what we need to know is that centripetal acceleration is also pointing downwards. And what's the normal force? It's pointing upwards, right? So what that means is that if theoretically this force right here, this force of centripetal acceleration, we need it to basically be the same as the gravity. Otherwise, because the normal force, we're going to see that basically our car is going to be lifted off. So what we're going to do is we're going to set gravity equal to force of accelerate or of centripetal acceleration, and I'm pretty sure we should get the answer, but not 100% sure. So let's find out. So we're going to say what this is going to be. We have our gravity. It's going to be mg is equal to m phi squared over r, right? Now notice the m cancels out. Now let's see, do we have a v? Oh, we're finding the actually we're finding the maximum velocity. Okay, cool. So then we have g is equal to v squared over r, and we have the r, right? The r is 60, so we're going to have 9.8 meters per second squared is equal to v squared over r, which is going to be 60 meters. And then if we do, once again, if we multiply this over, we're going to get meters squared per second squared. And what's the square root of meters squared per second squared? It's going to be meters per second, so that is the correct units. So if I do 9.8 times 60, and then we do the square root, we get v is equal to 24.25. What is this, meters per second? Final answer. Yeah. That is a good question. Let me think about this for a second. So when I looked at it, I just realized that basically at the end of the day, the force of gravity is the same, right? But do you know what the normal force definition actually is? Which we're actually going to do a problem that works with something similar to this. Right, it's the sum of all the downwards forces on the ground. So like for example, if we had something like this, right? And we were pushing it down, and then also there's gravity, right? And I don't know, let's just say this was a mass, right? Then the total force, normal force of this object would be this, plus gravity, right? However, let's say we have an object in the air, right? And we have gravity and this. Yeah, it has zero normal force. That's why it's going down. So with the same logic, let's say this car is not actually touching the ground, AKA, really realistically what this means is there's not enough force to balance out the fact that there's normal force. Now, let me think about how to explain this. I can kind of start seeing it clicking in my head conceptually, but I got to think about how to explain this like in words. But so if we have this normal force then, basically, if we don't have enough centripetal, or if we don't have enough centripetal acceleration, then what's going to happen is our car is not really being pressed into the ground enough, basically. And because it's not being pressed down enough, that normal force no longer exists. Because remember, our velocity, our instantaneous velocity is just going to be pointing here and here and here, right? So at this point, it'd be pressing like that. And did you want to add something? Yeah, I think that would work. Yeah, so like basically, I don't know if you guys in the Zoom heard what she was saying. She was saying, if we like set it up as F of n, the normal force is equal to basically the FG plus FAC, or not AC. Yeah. That is the same thing as basically what I did here. Because we are finding where the normal force is at 0, right? Because if we find where normal force is 0, then that will tell us the maximum amount of, or the maximum speed, aka the maximum right here of what we need to get without just like lifting off the ground. So yeah, hopefully that kind of makes sense again. This was a very confusing problem, I will say, but that's kind of why I added it. So the normal force, if we are only exists if we're pressing down on the ground. If you're not pressing down on the ground, you just happen to be like skidding, the normal force does not exist. And that's why you launch off into the air.
It's 0, wouldn't it? So FG would be negative.
Yeah, so like basically what this is assuming, right? Hold on, let me show you. So this is assuming that, let's say we had like no friction here for a second. If we stop contact, Miley, if we stop contact, look, then what happens to our normal force? Well, our normal force is going to be US times mg. So what happens to our normal force if we stop contact? Then it's 0. So we're assuming if we stop contact, which would be worst case scenario, then what acceleration do we need to basically stay in this centripetal motion and not go flying off? They would just basically be need to set equal to each other to be 0, right? So like, yeah. So once again, now if you had like, I don't know, maybe you want a Ferris wheel or something, and you're like at the bottom, keep in mind that now these would be like against each other. They wouldn't be the same direction. And so if you're at a Ferris wheel, right? Now, when you're on a Ferris wheel, the force of gravity is going down, meaning it is actually like the opposite of the force of gravity, or the centripetal force, which would be going up to the middle of the Ferris wheel, yes. Yeah, the FC is pointing to the center, you're correct. Oh, AC and C are the same thing. That's just my bad. I should have been writing them as the same, but yeah, sorry. AC actually means centripetal acceleration. I just accidentally wrote that as AC. Oh, so like AC, like just remember that F, but in this case, we see that the mass cancels out, so that's why it doesn't really matter. It's truly we're using the force, but in this case, the mass cancels out. So that's why like they're basically the same thing, because we don't need to know the mass.
So FC just means force, but this problem, the atoms cancel out, so FC just will.
Well, yeah, like basically, it's not that technically FC equals AC. It's that we don't need to know the mass to still theoretically find the value. The mass doesn't matter because it cancels out. Like we could technically put, if it told us to find the centripetal acceleration, right? Then we would need a mass. We don't know the mass, but notice we can, like whether this acceleration exists or doesn't exist, what we need, it's not dependent on the mass. It's completely independent. Y'all know, now you'll notice this. If they ever give you a problem where they, don't give you the mass, you can kind of assume that you don't need it to like solve the problem, I'm trying to think of a better way to explain that, but like, I don't know. Message me on Discord. Maybe I'll think of a better explanation. All right, so then we have 17. A block A with a mass of 2 kilograms is being pulled by a force F at an angle of 37 degrees, as shown along a frictionless horizontal surface. Oh, this problem is kind of juicy, guys. The block's acceleration is 2 meters per second squared. What is the magnitude of the force which the box presses on the table? Now, what did I just go over? What is the force that something is pressing on a flat surface? Bless you. But what is, like, we have something? No. It's not mass times gravity. It's normal force, which is usually mass times gravity. So it is the normal force. But think about this for a second. We have a rope. We have a rope, and this rope is going up.
Like mass times gravity and subtract from it, like the cosine for
Right. That's where you're at. We have to subtract. Yes. Okay. So we have this force going up, right?
You're saying regular. I don't think you're doing the rope.
All right. For this problem, we have a rope, and we have this rope at 37 degrees. Okay. And then we notice we have an X and a Y component of this rope's force. Okay. So our normal force is going to be equal to, basically, let's see. What are we looking for? Magnitude of the force which the box presses on the table. Yeah, that's our normal force. So it's going to be equal to mg, or rather our force of gravity, right? Minus the y component of the force of tension that this block is like, doing. So now what we're going to do, we're going to go with Fn. We're going to separate this into mg minus, now this force of tension of y. It's going to be, we have the force here of tension of this rope, and this is going to be 37 degrees. And we have a y direction, and so we have force Ty is equal to force of tension times sine of 37 degrees. Okay, so we have mg minus the force of tension sine of 32 degrees. Yeah, 30, did I write 32? It's 37. Yes. So like gravity is going to be 9.8 times the weight, no matter, or 9.8 times the mass, no matter what. That's always gravity. The normal force, or the force that it presses on the table, is going to be gravity minus any forces that are pointing up, plus any forces that are pointing down. So like, for example, if I put my phone right here, I put it on the table, right? The only force that is acting upon the table right now is gravity, right? If I start pushing my hand down on my phone, how much force is being pushed into the table? It's both the force of gravity from the phone and my hand pressing on my phone. But in this case, it's like doing the opposite. We're pulling this partially up with a string. So notice now the total force pressing on the table is not the force of my phone, it's gravity. It's the force of the gravity minus however much force I'm pulling up slightly, which is what we're doing with this string. Yeah, the string is pulling up. Yeah. Yeah. Let's see. So let me get my pen back. And so we have this, and this is going to be Ft sine of 37 degrees. Now this tension we know is going to be, so notice here, guys, we are given the mass actually, 2 kilograms, right? I have a feeling we might not need this mass. But let's see, we might need it. No, we're going to need it. So we have mg minus Ft. Now, what is Ft, right? The force of tension. And we know that this is going to be m times whatever acceleration it is. And notice that we have the block's acceleration, right? Right here. So we're going to have to do like m times the acceleration would be this total force, right? Or rather, yeah. And we have sine of 37 degrees, right? So we're going to do MA sine of 37 degrees. Let me check my notes here to make sure I have this fully set up correctly because I don't want to mislead you guys. It works. Oh, you already checked it. Okay, cool. Awesome. So we have mg minus MA sine of 37 degrees. And we're going to have, so notice we can take this M out and we can basically make it 1M. And we're going to do gravity minus, we'll plug in, or we'll be a sine 37. And we're going to have M, or actually I'll start plugging stuff in now. So we're going to have 2, 9.8 minus, and then it's going to be the 2 sine 37. And then this is going to be equal to 37 sine times 2. We're going to make that a negative, add the 9.8, and then times that by 2, and we get 17.19 newtons. That's our final answer, 17. Cool. Okay, there's, yes. The force of gravity is positive because I basically said, okay, like basically, it doesn't really matter whether it's positive or negative. What matters is if I say that this is positive, I need to say that this is negative. If I say that down is negative, I need to say that up is positive. This is a force upward, this is a force downward. Technically, it really doesn't matter because that depends on what's called your frame of reference. If I really wanted to, I could say down is positive and you'll still technically get a correct answer. However, most people say down is negative because it makes sense, but it's technically not required. Yes. What parts are? Let's start here. Okay, say it one more time. I just can't hear it. Oh, Fn. So the normal force, like the definition of normal force, is basically how much force a flat surface is basically pushing up, which is equal to the amount of force that you're pushing down into it. So it's like when I was showing my phone, or like, it doesn't matter what object I use. Like if I put my phone down right there, the total force downward from my phone onto this table is just the force of gravity, right? Now, if I push on my phone, the total force being pushed down on this table is force of gravity from my phone and however much force I'm putting into my phone. Now, if I pull this up, the total force of gravity, or the total net, force being pushed on the table, which is the same thing as the normal force, is, if I'm pulling up slightly, it's the gravity force of my phone minus the force that I'm pulling up with my arm. And basically the normal force is equal to the force that you're pushing it into, just negative. It's just flopped. Because at the end of the day, is my phone moving? No. So what's the net force in this direction? 0. Say again, sorry. The magnitude. So like the magnitude, when you're doing a one-dimensional problem like this, basically, if you have any negatives, you just make it positive. Because this is really a one-dimensional problem. If this were a two-dimensional problem or something, then in order to find magnitude, also there's a up here. But in order to find magnitude in like a two-dimensional problem or something, then you'll have to use Pythagorean. Same with like three-dimensional, you might have to use like expanded Pythagorean. Yeah. Yes. Did you guys hear what he said? If you have something pulling up, then any answer that is greater than mg will be wrong, because like if it's pulling up, you're going to subtract something. If you have something pushing down, any answer less than mg will be wrong. It has to be greater for this type of question. Okay. This is another question that can be really easily a trick question, which is why, once again, I included it. The reason that this question is a trick question is because it gives you extra information that you don't need. So it says a boy in a hot air balloon leans over to the side and drops a stone. At the moment he drops it, the balloon has, taking up to be positive, velocity is 3 meters per second, and acceleration is 2.5 meters per second squared. He notes that it takes 3 seconds to hit the ground. How high in meters was the balloon off the ground when he dropped the stone? All right. So what are we looking for here? Any guesses? the distance, it's the change in y. Now, if we throw a stone out, well, we know that its initial velocity is going to be this 3 meters per second, right? But if we throw a stone out and all of a sudden it's going to be free fall, it's just in midair, what's the acceleration going to be? 9.8. So this is why this is a trick question here. They give you this acceleration of the balloon is 2.5, but that means nothing into regards once we drop the stone. Once we drop the stone, it's no longer on the hot air balloon. This acceleration means absolutely nothing because the stone's acceleration is now 9.8, negative 9.8 if you want to make it down negative. So basically, we're just going to solve this like a normal kinematics, 1D kinematics problem, just assuming that the acceleration is negative 9.8. And we're going to do nothing with that 2.5, but I think this type of question would really mess people up because they're going to be sitting there like, how do I use this 2.5? Well, the answer is you don't. But it's there just basically to trick you. So let's see, we're going to say, I'm going to use this equation because I think we have all the stuff for it. So we're going to do, this is initial in the y, t, or rather, no, I'll take that back. No, we're going to use a different one because we don't have time. So eraser, maybe we'll use this one. What if we did, wait, oh, I'm blind. It's crazy. We actually do have time. Okay, so we have time. So we're going to do, it's crazy. All right, so we're going to do, yeah, he dropped it. It's still going to be 3. The initial velocity when he drops it is still going to be 3, but the acceleration will be negative 9.8. If I'm moving, right? Look. Well, actually, let's see. If I can do this really quick. No, I don't want to use the electric pen though. I don't want to break this thing. Hold it. Let me use a normal pen that cannot break. Okay. If I have my hand, right, I'm going to try to do this really quick. Otherwise, it's not going to work, right? If I have my hand, I'm going to move up, right? And then I'm going to try to really quick move my hand out from under the pen without, like, you know, pushing it a ton or something.
You have to be moving up.
I gotta be moving up. Oh, wait, you're saying like this. Oh, okay, I see what you're saying. All right, so if I take this pen, right, what I want to, okay, if I take this pen, right, when I let go of it, you're going to notice for a little bit of time, it's still going to be going upwards because the initial velocity is the same as whatever my hand was going to be going at. So if I take this real quick, see that? It was moving upwards for a second. So yeah, that's how we know the velocity is like, the velocity is still going up for like a bit. But notice it makes a parabola shape because it's going down. Yeah, what's up? Yeah, you're right. I believe you actually taking up to be positive. So because it says taking up to be positive, and then it gives us a positive velocity here, that means that it is going up. Well, I think because it says this right here, you can. You're saying like, you know, I see what you guys are saying. I probably see, and I guess this is just bad wording on the problem then. Like, it should just say moving up 3 meters per second. If it is that basically what you guys are saying? Yeah, I see what you're saying. Like, yeah, but also it's not like I wrote this question. So yeah. It just kind of is what it is. So anyways, we're gonna solve this real quick. I'll get this done quick. Let's see. So we're gonna say v initial y time plus 1/2 negative 9.8 times squared. So then we're gonna get change in y is equal to the velocity initial is 3 meters per second times the time is 3 seconds plus 1/2 negative 9.8 meters per second squared. Time is going to be 3 seconds squared, which is going to be, let me solve this real quick. So it's going to be 3 times 3 minus, because the 9.8 is negative 9.8 times 0.5 times 9. We get, so the change in y is going to be negative 35.1 meters. Now, does that make sense? Think about that for a second. We know that it's 35, that's the answer, but does it make sense that it's negative? Yeah, it does, because hot air balloon's in the air. So, and earlier we defined down to be negative. So what this is actually going to mean is if we take the magnitude of this, we get basically the distance is equal to 35.1 meters. That's our answer right here. Let's see, how many more slides? Only 2 more slides, guys. 2 more slides. So because of friction, a block of mass 5 kilograms is stationary on a horizontal table, even though the force of 10 newtons is applied to a block at the angle 37 degrees below the horizontal. Coefficient of static friction between the two is 0.6. What is the magnitude of the force of friction? Okay, so we're going to say the force of friction all right, so the force of static friction is going to be, we know that the total, the maximum, right? Or rather, yeah, the maximum force of friction, or rather the force of static friction is less than or equal to US times the normal force, which is mg. So we know that the force of static friction is less than or equal to 0.6. And then m says 5 kilograms, and g we know is 9.8. So the force of static friction is less than or equal to 0.6 times, what did I even write there? It's at 5 kilograms, yeah. 0.6 times 5 times 9.8. So we know that the maximum static friction force is 29.4. Now, what if I solve this now, and I notice that the force that is being applied is more than 29.4 newtons? What does that mean? That means it would be moving, which would mean that in order to solve this problem, we would actually need the coefficient of kinetic friction. Now notice that we don't need the coefficient of kinetic friction because it's not given to us. So that means we can probably assume that it's not moving, but we'll just solve it real quick. Let's just see how much force. Now remember, the force of static friction is going to go opposite of the motion. Obviously, it's not moving up or down, right? It's probably going to be either moving this way or this way. So we're going to take the force, which is 10 newtons. And so we have 10 newtons being like this. And which component are we looking for, guys? I kind of just set it up here. It's going to be moving either left or right. So just say that's what we're looking for. Now, this is such a terrible drawing. Hold up. And then this would be 37 degrees. And let's just say we're solving for A. So what is A equal to? Well, this is actually going to be the force in the x direction, right? So you can see this force is an arrow that's pointing down, right? And we can see it's at 37 degrees. So then if we make a triangle here, we can see that the force in the x direction is going to be right here, and this is going to be the force in the y direction. And we're looking for the force in the x direction, because that is what is going to be the opposing force to the static friction, assuming it is not moving. So basically, we're going to get 10. Now, if we look at this triangle, right, sine would be getting this right here, but we're looking for A, right? So now we're going to use cosine.
Wait, so then math and gravity and
This would matter if we get an answer that is greater than this. But if we get an answer that is smaller than this number right here, then our answer is just whatever we get. So we're going to say 10 times, well, actually, let me just solve this. 10, where's my calculator? Here it is. So cosine 37 degrees times 10, we're going to get 7.986. Newtons, which is our answer. Now, why is that our answer? Because this force is less than how much static friction is able to basically occur. So because that is how much the total static friction is using to stop this block from moving. Yeah, it only needs 8.
static friction like also the normal.
Static friction goes up to the normal force times the coefficient. It goes up to it. It is not the same thing. Instantaneous, or rather like the static friction that is happening at that time, is always less than or equal to the coefficient times the normal force. Yes.
Okay, so maybe I missed this when you were speaking, but for the first part of the conversation, when I'm thinking normal force, I'm thinking whatever is moving in the y direction, right?
Yeah.
Does that include the component from the force, the y component, or does that not matter?
Here's the thing, let me think about this for a second. This is actually a good question, because I want to try, let me do something real quick. Let me check. It actually might be, so if we did 10 times 37 sine, we get 6, right? And I'm going to check by doing it that way and see if you still get the correct answer real quick, okay? So what we would have is we would have 10 times 37 sine, we get 6 newtons. So then we would have 4 newtons, right? Like total, or rather, wait a second. That force is going down, so it would actually be 6. You can see how, you can see 6 plus. Let's see, so if we do, once again, so 37 sine times 10, we get 6. So then that would be plus the 10 that's going down, right? And that would be the normal force. Yeah, you're right. So basically what this would mean, hold up. The normal force was actually this plus the 6 or so newtons here. So it'd actually be plus 6 newtons, plus 6 newtons. So the actual maximum, you're completely correct, is actually equal to like, what is that, 35.4-ish, around there. Does that make sense? The 6 is the force pointing down from the force. So she pointed out, she was like, wouldn't the maximum actually be with that 6 added? And yeah, when I thought about it, yeah, that's actually correct. So that's actually the maximum because we have that force going down. Say again?
Minimum.
Yeah, that only needs 8, so it's still only using 8, yeah. But 8 is obviously the correct answer, and this is still how you'd solve it. But this is actually what you'd be using to check. This original 29.4 figure was wrong. So yeah, that's that problem. Any other questions on that? Last one. Unfortunately, I saved like one of the hardest ones for last. So hopefully I don't mess this one up while like doing it, but we'll figure it out. Let me think. Let me read this one real quick to myself. Block A with a mass 3 kilograms rests on a horizontal top. The coefficient of static friction between surfaces is 0.8. You attempt to pull a block using a string at an angle of 40 degrees above the horizontal. What is the magnitude of the force in newtons? Oh, okay. I think I know what to do. So let's draw a picture. We have this thing, right? And this is 3 kilograms. And we have a little string. Then we have a string that is about 40 degrees. That's probably not 40 degrees, but we're just going to say it is. And this string is, let's just say this is our net force, or what do we want to call this? Force of tension? Yeah. Okay, force of tension is right there. And we know that our static friction coefficient is 0.8. We're wondering what is the magnitude of force in newtons necessary to put it in motion. So in order to put this thing in motion, we're going to say basically the force is going to be equal to the force of static friction. Now remember, the force of static friction is less than or equal to, the constant times the normal force. What happens if it becomes greater? Then we start moving, right? So what that means is that if we set this equal, we can basically see like the minimum force to get it moving. So what we're going to do here, we're going to take, let's see. We're going to take this force. We need, which way is the force of static friction going if we're pulling this way? Which way is static friction going to be pulling? To, yeah, the left. So we know the force of static friction is going to be going this way. And we basically need that to be equal to, the force of static friction needs to be equal to Well, what's this component of force right here? This, we're saying that this component needs to be enough to take out this, right? Because that's in the same direction. So what's that component right there? Yep, FT cosine 40. Now, we're gonna have to find this FS, right? Now, in order to find the FS, we have to say that this is gonna be, we're gonna plug this in right here. We're gonna say US. Now, what's the normal force? This is the tricky part. What's the normal force here? It's not just mg.
The
Yeah, it's mg minus the y component, right? Because the y component is going up, which means that it's going against the gravity, not with it. So we're going to do mg minus, and this would be ft. So if this is cosine, this must be sine, right? And then we're going to go equals ft cosine of 40. Right, so now we have a big long thing, but we're going to use this. So we're going to have 0.8. And we're going to do mg. So m, does it give us the m? Yeah, it gives us 3 kilograms. And then gravity is 9.8 meters per second squared. And then minus, we have to distribute this, remember? That's what I'm doing right now. So it's going to be minus 0.8 F, force of tension sine 40 degrees, equals force of tension cosine of, what did I just do? That's crazy. Okay, cosine of 40 degrees. So then after that, we're going to try to make the force of tension just be on its own, right? So I'm going to move all of this stuff to actually the right side. And I'll just actually calculate that real quick. 0.8 times 3 times 9.8. It's going to be 23.52. If we want to make, let's see. Yeah, it doesn't matter what, like we can say gravity is positive as long as we're saying that this force right here is negative. Or you can say that gravity is negative, but if you make gravity negative, this would become a positive, just so you guys know. So we're going to say 23.52 over here. That's what you get when you plug in this. And then we're going to add this over to the other side. And we're basically going to get 0.8 F of t sine of 40 degrees plus ft cosine of 40 degrees. Right. And then notice we can factor out F of t and we get 0.8 sine of 40 degrees plus cosine of 40 degrees. So then after that, we're going to get, if you just take this and you divide them, so we get ft is equal to 23.52 over, so we get 0.8 sine 40 degrees plus cosine 40 degrees, which is equal to got 18.37. And they must have had a rounding error while making this because I didn't, 23.52 was an exact answer. So this is actually like very exact right here. So I guess it'd be technically 18.4, but 18.3. That's how you get that answer. All right, so that's all the slides. Thanks everyone for coming. I guess best of luck on the exam tomorrow. And I'll see you guys, I don't know, I guess all tomorrow. Peace. You guys are welcome. I'm going to close out the Zoom. All right, see you guys.
Why are you? No,
I have to take it. Wait, I gotta stop the recording. Hold on.
yeah.